One general theme that we've been looking at when looking at deep learning and deep neural networks is the way the networks are creating representations of the data in the different layers. In the previous lecture, we saw this explicitly in the case of autoencoders, where we are using the network to create a useful representation, even without any target for classification, regression, or something like that, but only using the unlabeled data. We're now going to take a step back here and look at this general problem of representation learning, or finding these representations in a more generic way. So the motivation here is that the features we are going to use for some purpose are very important. So abstracting from machine learning and so on, without even considering these kinds of problems, just think of the difficulty of doing dividing two large numbers using Roman numerals. This would be very hard to do. If we use the Arabic numerals that we generally use, then the algorithm becomes much simpler. In machine learning, finding the correct features or the right representation can make the task much easier to solve. So we can see deep learning as stacking feature extractors until we get the correct representation for the final part of the network to do what we need. And we even saw this clearly with the convolutional networks used for classification, where we use several layers of convolutions to extract the right features, and then we just add one or two layers of fully connected neurons to do the classification. So the idea here with representation learning is that if we have limited data for some supervised learning task, and we often have limited data because supervised learning requires labeled data and that tends to be expensive, then we can have overfitting when we train our models. But if we first learn the best representation of the data with unlabeled data, we can use lots more data, many more examples, and reduce the problem with overfitting. So we can use unsupervised learning or semi-supervised learning to help find the right features. So these are some assumptions that we can think of when trying to find a good representation for our data. So first of all, we know that data is not randomly distributed over all the dimensions of the feature space. This is the idea behind manifold learning, because the actual data does not have all possible combinations of our input features, but only occupies a defined subspace of all those combinations. For example, not all possible combinations of pixel values are images of cats. In fact, if you create random combinations of pixels, you will almost never have a cat in that image. So cat images are a very, very small subset of all possible images. And so cat images will be distributed along a manifold that can be of a much lower dimension than the space of the input images that we are using. Another idea is that often we can generate data, or we can consider that the data we have in some particular problem is being generated by a small set of independent factors. Even though the data has lots of combinations, these can be combinations of these independent factors if we could identify them. For instance, when we have handwritten digits, we have some combinations of things like the color of the pen with which we are writing, or the size of the digit, or the thickness of the line. But these are independent factors. They are not related to each other, which means that you can write with a red thick line or a blue thin line, or any combination of those, and still have valid data. These explanatory factors or concepts that are behind what we can use to describe the data also tend to have some hierarchical organization. We can go from small, more elementary concepts like contrast, color of pixels, edges, and so on, up to higher patterns if we are dealing with images, for example. And another thing that we is generally true is that unlabeled data is much more abundant than labeled data. So basically, all these aspects of the manifolds, of the entanglement of different features, and the hierarchical organization of these aspects, they are all present in unlabeled data. We don't need labels to find these aspects and to try to represent them accurately. And this is a good thing because unlabeled data tends to be a lot more abundant. So another thing that we can look at in this representation learning is not only the shape of these patterns in the data on one particular problem, but also that some aspects that are important in one problem may also be important in a different problem. For instance, problems of image recognition, when we are trying to recognize faces or license plates or handwritten digits or things like that, even though these are different problems with different sets of data, there are some aspects that will probably be important in all of these. For example, detecting edges, detecting the orientation of some lines, contrasts, and things like that. They can probably be useful for all of these different problems. Another aspect is that when we are looking at each example, when we have to train our models or even consider just a specific example, we will only find some of the relevant factors for the whole data set. So this is another reason why we may want to find a good representation using, for example, unlabeled data that is much more abundant, instead of relying on a smaller data set of labeled examples, because not all the examples will have all types of ears, tails, legs, and so on. The different combinations of features or even different instances of some features will not appear in all examples. And the function that we are trying to learn to map from some input into some output, for instance, in regression, in classification, or even in the special case of autoencoders, this is obvious, but even in a case of classification, will tend to be smooth. In general, we don't want a very tiny change in the input to result in a very different output. We want similar inputs to result in similar outputs. So these considerations mean that if we can extract these regularities, if we can extract the features that meet these criteria, give us a smooth mapping, represent the manifold of the data, represent those independent aspects that contribute to the data, and so on, then we'll have a representation that is very useful, not only to help us solve a particular problem with, for example, a smaller data set that we are going to use for classification because it's labeled or something like that, but even useful to solve similar problems with different data sets, but that can retain many of the same features. So this is the general idea behind representation learning, trying to find these aspects of the data that can be useful for more than just a simple application on a particular data set. So let's start with the unsupervised pre-training. This is one example here. This was actually used in about 10 years ago, 7 years ago, something like that, was one of the methods used to train deep neural networks, in which the layers were trained one at a time with unsupervised pre-training, where we are going to train a layer like an autoencoder. The layer will be the latent representation of the autoencoder, and we are passing all our data, even unlabeled data that we have, we are passing through this autoencoder to create a useful representation in the latent space, so in that hidden layer. For example, we can train it as a denoising autoencoder, where we keep adding noise to the data and we obtain a good representation of the data in that layer. And now what we can do is we throw away the decoder and use the encoding of the input as an input to the next layer, which is another autoencoder that we're going to train in the same way, but instead of feeding directly the inputs, we are going to feed the encodings generated by the first layer. And we keep doing that, and so each layer will be trained isolatedly, alone, without supervision. It will be trained as the central part of an autoencoder, but each one is being trained on the output of the previous one. And then we can stack them all and fine-tune with backpropagation, because in this way we are training each layer to try to find the best representation of the data that is the encoding of the previous layer. Now, the reason why this was used historically is that basically we, before using rectified linear units, if we were using only sigmoid activation or hyperbolic tangent and so on, it was very hard to train deep neural networks because of the vanishing gradients problem. But using this kind of initialization, using unsupervised learning for each layer, we had this regularizing effect where we started not at a random position in the space of parameters, but we always start at this different region of the space of parameters, but one that was already adjusted to some aspects of the data. So learning this distribution of the data by unsupervised pre-training of the different layers helped find useful features right from the start, and thus was useful for training the network for supervised learning. And we can see this effect of the initialization. So you can think of this when you are trying to create good representations for example, text documents or things that are very, the data is very sparse. For instance, there was this experiment with a data set of human actions measured by different sensors to measure the movement of humans. The data had 5,000 dimensions, but for most of the examples, the majority of these different attributes was at 0, and only a few were not 0. So we have a very high dimensional space, but training these denoising autoencoders with regularization, these layers manage to capture better the manifold of the data. So you can see here, even compressing after from those 5,000 dimensions to a few dimensions, we can see different patterns in those human activities. So the idea here is that we can have a starting point for our network that was created not by random initialization of the weights, but by pre-training the layers in order to make them find some good representations of the data. And for the first layer, the data is actually the original data set, but for the subsequent layers, the data for each layer is simply the output of the previous layer. So this way we can create a stack of denoising autoencoders that starts, even before training the complete network, already starts with some useful representations. So this is an example of a paper that tested 50 networks with pre-training and without pre-training. And we see here manifold projections of the trajectories during training of the weight. So we can see the way the networks start and their trajectories during the training. But networks with pre-training follow trajectories in a different space of the parameter combinations than networks without pre-training. So this is a manifold projection with TSNE, T-distributed stochastic neighbor embedding, which tries to preserve distances in the neighborhoods, but not outside the neighborhood. So basically, it favors the probability of finding the same neighbors in the original high-dimensional space and in the projected space. So here we can find networks that had a similar trajectory in the parameter space to be represented close together, while others with different combinations of parameters can be further apart. But if we use an isomap projection, we see that the trajectories of networks with pre-training are all very similar, because isomap now preserves better the distances over large scales. And we see that without pre-training, these trajectories are very, very broad and very spread out. So we see that pre-training has this regularizing effect in that it makes all the networks start in a different but smaller subspace of the combination of parameters. So this was one way of using pre-training and supervised pre-training to start the training of the network and then continuing with backpropagation and supervised learning. This is mostly important for historical reasons, because it was a practical way of training deep networks before using rectified linear units. With rectified linear units, dropout, and other regularization methods, now this is not as useful, and it's not very practical to use unsupervised pre-training in this way, because with rectified linear units the vanishing gradient problem disappears, and with other regularization techniques that are very successful, the regularization effect of pre-training is not particularly necessary, because we can use dropout and other regularization methods. It can still be used in some applications where a large number of unlabeled examples can be used to give a head start to how the network will be trained. So unsupervised learning, unsupervised pre-training with many examples from texts that you can find in the internet or anywhere, even without labels that you're going to use for natural language processing for classifying texts or things like that, can be used to build these first embeddings, these representations that are a lot more useful for whatever supervised learning task you have at hand. Another thing that is important here, the idea of transfer learning, is to use whatever we learned for a particular problem to give us a head start in a different problem. For example, suppose that we have a network trained to distinguish between cats and dogs. If we now have a problem of distinguishing between horses and donkeys, the low-level features are probably the same. Edge detection, shapes, colors, things like that. Maybe we only need to change the higher layers on the classifier. So we could use most of the network trained to distinguish between cats and dogs, and just change the classifier at the top in order to, for example, the dense layers at the top, in order to change it to distinguish between horses and donkeys. Or it could happen the other way. We could have a shared representation at a higher level, but differences at the lower level. For example, in speech recognition, we need to recognize the structure of sentences, different words, how the words combine together to give some particular instruction or something like that. and this is the same for all speakers of the same language. However, the voice of the speaker, so the identification of each particular token, will probably have to be learned for each individual speaker. And this is how many voice recognition systems work, where the person has to train the system to understand how that particular person speaks the different words, but then the top part, the more higher level representations are the same, and those models will not need to be retrained for different individuals. There are several different aspects to this idea of transferring knowledge from one problem to the other. Sometimes we can be transferring in the same domain and the same type of problems. Sometimes we have the same kind of problem but in different domains. For example, in sentiment analysis, this is something that is increasingly used. We use automated systems so machine learning and deep learning, to try to classify the sentiment of the person who wrote some comment, some product review, something like that. So we are trying to figure out if the person was angry, was pleased, was happy, and what the person was feeling when writing that. Now we can have a model trained for example, reviews of movies and songs, and we may want to apply that to electronics, to an appliance store, and this way we have to apply this to a slightly different domain, but the mapping between specific expressions and words to happy, unhappy, pleased, displeased, angry, and so forth should be the same. So in this case, maybe we could use autoencoders to do create a useful representation of the texts in general, and then train only the upper parts, the parts that follow from that, for the different domains. So in this case, we would be adapting the same kind of model and the same system to the different domains, and minimizing the amount of retraining that we would need to do to go from one domain to the other. Another problem in practice that occurs, where we can try to adapt our trained models to different conditions, is concept drift. This occurs when we have gradual changes over time, either because there are changes in the way the inputs must be mapped to the outputs. For example, suppose that you are trying to predict credit risks from your customers, when the customers wanted to buy things from you and with credit, so they would pay later. Depending on how the economy is better or worse, then things like having a job, having some certain income, having a car or something like that can be or not reliable indicators, depending on the overall state of the economy. So the way you're trying to make this prediction based on attributes from the person may have to change gradually as the economy changes. Another thing that can happen is the actual distribution of the examples is changing. For instance, you start with a shop that is very specialized and has a particular kind of clients that are really interested in whatever you're selling, say board games or something like that. But then your shop becomes very popular, you open several stores, and now you are catering to a much different customer base, and so you may need to adopt your models to this change in the distribution of the data, because now the examples that you are classifying when you try to predict which are the most valuable customers, which customers you should target with advertising or things like that, those things may start changing because the distribution of the customers is changing. So you have, in the case of concept drift, an example of the conditions changing, but you may not need to retrain everything from zero. You can still take advantage of what was learned previously and just adapt it slightly to the new conditions. So basically we have this idea of using previous experience under new circumstances and without having to retrain and learn everything from zero. And we can also apply this to these kind of examples, one-shot learning or zero-shot learning, where everything was already learned with different data, different conditions, but it can just simply be applied to the new circumstances. For example, in this paper you can find an example of this. There was first unsupervised learning of the manifold of words. So we have here a manifold projection of different words, many different words, using unsupervised learning, just looking at the structure of the words. This can be done by looking at what words go together in similar contexts, the neighboring words and so on, and we use that to map words into a dense representation that represents this hypersurface. And then we can use supervised learning to map between a set of labeled images and particular words. So we have a horse being mapped here, dogs being mapped here, and so on. Because we know which words correspond to the image, and we use this supervised learning for that. And now we can do zero-shot learning by having a completely new word, a new image. This image was not in a class that was previously considered. So the word this image maps to was not present in the data set. But since it's present, it was not present in the data set on the supervised mapping, but of course it was mapped in the unsupervised learning into the manifold. And now when we present this model, this trained model with the image of a cat, we already have a projection into the word manifold that is close to the position of cat. And we can find the word corresponding to that image, even though we never trained the model for cat and the association with these kind of images. So this is an example of transferring from what was learned in different data sets into new data and even new categories, so to speak, that were never found before. So basically we are going to take advantage of what was previously learned, and for the particular example here, we are going to today in the exercise you're going to use part of a model that you trained before and apply it now to a new problem. You can do this in Keras easily. You can find here in I think the URL is outdated now, but if you look for Keras applications, you can find a list of pre-trained neural networks, some of them very large, for image recognition, that you can download with the weights. So you have the hypothesis, the instance of the network already trained, and you can use that for different problems. But you can do this in many different contexts, training different parts of the model that you're going to use on different data sets, training a model for one large data set and then applying that for a data set that is not so large but maybe similar, so that you don't have to retrain the whole model and so forth. So this would be the idea of transfer learning, and you can do it even with supervised or unsupervised pre-training. So this is what you're going to use in the first exercise, supervised pre-training, because last week you used a convolutional neural network for classification of the fashionista data set. So you're already trained your network to classify these images. And now what you're going to do is to use most of the network already as is trained to help you classify the NIST dataset. So for this we're going to use the functional API in Keras because we need to manipulate the models a bit more flexibly, and we're going to use the pre-trained model from last week. So what we're going to do is we're going to create the same model now with the functional API. and we're going to load the parameter weights, the parameter values, the weights from the model that we trained last week. If you did not train your model on the fashionista last week, then start the exercise today from that part, so that then you can do the transfer learning. We're going to freeze all the weights of the convolutional part. We're not going to retrain these. These are going to be fixed, and we're going to create only the dense layers for the classifier and just train those on NIST. So basically, we are going to use the convolutional layers for feature extraction that were already trained on fashion NIST. They will extract the same features on NIST, and we're going to retrain the dense layers in order to classify the digits using these features that were already used for the clothes drawings. So to do this, we're going to use the functional API, but we're going to start in the same way as we did last week. We're going to import the data set. Note that now it's the NIST again, not the fashion NIST that we used last week. We're going to reshape the images and rescale them. Now, if you do this, you normalize everything for a range between 0 and 1. If you did this last week, if you didn't divide by 255, then don't do the division now, because otherwise you'll get images in a different scale than the one your previous network was trained for. So do it the same way as you did last week. In this case, we don't use standardization because this operation will already put everything in a range between 0 and 1, so we don't need additional rescaling. Now we're going to use the functional API to create the same model that we did last week. And the functional API is simple to use also in that all the layer objects, so those layer objects that you were creating in the sequential API to put into the model using the add method to add new layers, these objects are callable. They implement this call method, so they can be used as functions in Python. And so the way we create a model using the functional API is we start with an input layer. This input layer simply creates the tensor for inputting the data, and here we can specify the shape of the examples. In this case, it's 28 by 28 by 1, which is the shape of the matrices that we're going to use to represent the images. We can give it a name so that it's easier to find then in the model when we want to connect it somewhere. And now we just add new layers by using each type of layer, each layer object. For instance, here a two-dimensional convolution with 32 filters, 3 by 3 kernel, padding same. Here we don't need the input shape. This is unnecessary because we're going to apply this one to this tensor here. That was the result of this input function. So when we call these layers, we can add send as argument the output of the previous one, and here we store the output of this convolution 2D function applied to those inputs. We store it in this variable, and now we use it as the input for the activation function. So we create a ReLU layer, a ReLU activation here, and we use this object as a function that receives as an argument the previous tensor, and we'll create we are going to chain all these layers in a sequence by using the output of the previous one as an input to the next one. So for this kind of stacking layers, this works the same as the sequential API. We are just stacking one layer to the other. But this functional way of connecting the layers gives us more flexibility to do different things. And this is what we're going to do here to solve this transfer learning to solve this problem of classifying NIST with transfer learning. So continue, create all the model that you had before, including all the dense layers, because you need everything to load the weights. In order for you to load the weights from the previous exercise from last week, you need to have a model that is exactly the same. Otherwise, Keras cannot match the weights to the correct layers. But what we're going to do is, after you do all the convolution layers, so this is not complete, there are a few others here. This also depends on whether you use dropout or not. If you did not use dropout on the convolution layers, do not include it now. If you used it, then include it now, but do the same model, the same layers exactly, including the multi-layer perceptron at the end, so all these dense layers that are doing the classification. Then we're going to compile the model, and to do this we have here a chain of layers that are used as functions on the output of the previous one. And now we can create a model by using as input the first layer here, and as output the last one here. So Keras knows that the computational graph for this, because all of these layers were connected to each other when we called them as functions using the previous ones as arguments. So this will be the complete model exactly like we created last week. We're going to compile it, but we are not going to use it. So I just compiled it with a stochastic gradient descent and a mean squared error loss, which does not make sense for the classification model here, but this is irrelevant because we are not going to use this model completely. We are just compiling it in order to load the weights and then freeze everything. So this is what these instructions are doing, loading the weights into the model and then looping through all the layers of this old model and setting the trainable flag to false. This tells Keras not to change these weights during training. So we are freezing the old weights obtained by via the training from last week. And now we're going to create our new model. Here we gave a name to this particular layer. We have a layer here, the flattened layer, which, if you recall, is what we use to pass from the convolutional part of the network into the dense layers. We need to flatten the feature maps first. So we're going to call this layer the features layer. And now we're going to create a new model by starting a new branch here that creates a dense layer, but starts with the features, with the output of the features layer of the old model. So this will be the input tensor into this dense layer. And this is from the old model. We get the layer called features, which is this one here. And we get the tensor that is output from this layer. And this is what we're going to feed into this dense layer that is now different from this one. We created this one by putting as input the output of this function. But now we're going to take the output of that layer into this one here, a new dense layer. And now we're going to build the rest of the classifier, the activation, dropout, batch normalization, and softmax. And we're going to create a new model that uses the inputs from the old model. So this inputs layer is the first layer that we created here. So the input is the same. It will then go through all the convolutional parts in the computation graph, but then we get the output from this one here. So it means when it reaches that flattened layer, the one we called features, it will shift to this set of layers, and it will not use the original ones which had the original weights. So basically what we are creating here is a new network that uses the convolutional layers of the old model from last week, creates a new set of dense layers for classification. The convolutional layers of the old model are all frozen, they will not be trained, but these new layers are trainable. So this is what we are going to train now. And if you compile the model, we create now a new optimizer. So we're going to use momentum and stochastic gradient descent. We are going now to compile this with the appropriate loss function, which is categorical cross entropy, because this is a multi-class problem. And if you do this, called the summary of your new model, you see that you have one large set of trainable parameters. These correspond to the dense layers at the end of the model. But you also have these 60,000 non-trainable parameters, which are the frozen parameters in the convolutional layers. And now you can train this and compare the time it takes to train, the performance, and so on, with the alternative of training everything from the start with the MNIST dataset. The second exercise you're going to do this today is to use an autoencoder and compare the autoencoder with PCA for the banknote dataset. So you can use this dataset from the previous exercises. You can try different architectures. For example, this is one example. I used here Leaky Relu and Adam with the learning rate, with a small learning rate. Or if you rescale the inputs, maybe you can use a larger learning rate, but you can experiment here. Also experiment with different architectures. Look at the validation error to see if you can find a good autoencoder, and then compare it with PCA. So you can use from scikit-learn PCA, just use two components and use principal component analysis to project the original data into 2 dimensions, and then you can see the results. So this is one example. It may not be exactly like this. PCA should give you something like this. Your autoencoders will vary, depends on the what encoding you're on, the architecture, on training, and so on. Remember that this is stochastic, so it will not be always the same, but you can experiment with different autoencoders, different number of epochs, and try to get a feeling for how this works in this exercise. Okay, so this is the end for this block. After the test, you're going to start with Professor Rui Rodrigues with the final assignment, so it will be more oriented to actual problem solving and not so much theory as this first part. In the next session, it will still be with me, so next week we will have no lecture. I'm not going to use YouTube. We'll just meet on the Zoom meeting for questions about the test, the subject matter, and so on. So for anything that you need, we'll meet at 4 o'clock and we'll continue until nobody has questions. And then the test will be at 6 o'clock, so at the time of the tutorial. It will be online. Those of you who had machine learning last semester already know how this works. You'll have 5 questions, 10 minutes to answer each of them, and a 5 minutes break between the questions. Remember that you'll be scored on how you explain things, so be clear and concise and explain things correctly. And note that the questions may be larger than what you can do in 10 minutes. This is on purpose to avoid too much communication between you during the test. So just try to follow the priorities that I suggest in the questions. Answer the most important parts as well as you can, clearly, concisely, with a structured text. And if some things are left out, don't worry too much, because I will calibrate that in the grading. I will include during this week rehearsal for the test. So either tonight or tomorrow I will put a rehearsal version for the test. I think most of you already know how this works, but anyone who did not do machine learning last semester can rehearse the test in the next few days, and let me know if you have any questions about how the test will work, and I will clarify everything in time for the test. For now, download the version of the lecture notes for this tutorial. I updated some things today. I will try to add a few things in the next few days. There are some sections that are still missing, but I will try to do it maybe tomorrow or Saturday in time for the test. Okay. So that's it for now. We saw this idea of improving learning by trying to create better representations, either using unsupervised learning from larger data sets, or transfer learning when we try to adapt what we learned in one data set to another data set. There are some things here that are important in historically. For example, unsupervised pre-training of each individual layers is no longer used, but can be useful in some particular instances where you can use unsupervised pre-training to get better representations when you have lots of unlabeled data, and then transfer that into the supervised learning problem. So this is one, aside from the book, you can take a look at this paper. This is, although it's a bit outdated now, but it gives you a good overview of these different aspects and perspectives on representation learning. Okay, so I'll just log into Zoom and we can talk a bit there if you have questions. See you soon.